Hi, so I'm beginning a series of videos that are going to cover a very interesting sub-project for the IBM 1130, where I'm going to create a device that will allow me to put a disk cartridge in the disk drive but not actually use the heads. They won't actually touch the disk, so there's no risk of a head crash damaging the heads or the disk cartridge. Instead, this device I'm going to create will serve the data and capture any writes onto an SD card, an image of the 2315 disk cartridge. And because of that, it'll operate at normal speeds and be completely compatible to the software of the 1130. It will allow this museum that I'm restoring the 1130 for, and other museums, to have multiple disk images with diagnostics and demonstration programs where they can show off their IBM 1130 without having to use real disk packs or take any risks with the almost irreplaceable disk heads. So one of the things I needed to do was to make a decision about what components I'd use to build this virtual 2315 cartridge facility. I selected an FPGA board from Digilent that I've used similar boards of theirs before. This one is the Arty S7 using a Spartan 7 Xilinx FPGA. And I also am going to connect that to an Arduino, a Mega 2560. So I picked the 2560. I've used it before because it has plenty of IOs and is something that has other features that I find useful for this project. So the two are going to communicate. The Arduino is going to talk to an SD card that has different virtual cartridges on it. I can really store, thousands and thousands of virtual 2315 cartridges because they're only 1 megabyte in capacity. And that will talk over a serial peripheral interface, an SPI link to the FPGA, which is what's going to actually store the cartridge image and then interact with the disk drive, telling the disk drive that everything's good, watching what the disk drive is doing so that whenever the software does a seek, moves the disk arm to some cylinder or another, or selects the top or bottom surface, the top or bottom head, we'll know it and we can track that. I'm seeing the pulses that come from the actual spinning disk drive. That spinning cartridge is going to send me pulses that tell us where we are in the rotation. So armed with all of that, the FPGA can precisely model where the head would be over the real disk at any instant in time. And therefore, when the CPU does a read, I can start streaming the bits to it exactly as they would have been generated from the disk head. But by modifying the drive, I'm not allowing the heads to come down and touch the surface or float over the surface, so it's completely safe. Anytime the CPU tries to write to this disk drive, I'm going to be able to capture the stream that's being sent by the CPU and update the image on the FPGA of that virtual cartridge. Then when the disk drive's turned off, I'll unload that or send the data back up to the Arduino, write it onto the SD cartridge. So the SD cartridge image on the SD card is a faithful reproduction of what would have been on a physical cartridge if the disk drive were working as it's normally designed to do. So the SD card that's connected to the Arduino, it communicates through a software library that's been developed for managing the SD card interface. Unfortunately, that library is not very good at playing with other devices on the SPI link. So a serial peripheral interface link can have multiple slave devices connected to the master, and by changing the slave select line, turning on one at a time, you can alternate between which device you talk to. The problem is this software for the SD card isn't really written to accommodate that, and so it does bad things and doesn't allow you to share the SPI channel. One of the things that's convenient about the Atmel Mega 2560 chip that's on an Arduino Mega 2560 is that it has 4 universal serial synchronous channels. They're basically normally serial ports, but they're USARTs, not a UART, so that it can also do synchronous activities and has the capability with Atmel to turn it into an SPI channel. So you can set a bit in the microprocessor, and then it begins to use that serial port as a SPI master. So that's potentially a second channel. In fact, there are 4 of these USARTs on the Atmel chip. So there could be 4 separate master SPI channels in addition to the one that's normally used. So an SPI channel has a port that sends bits out from the master, a signal line that takes bits back in from the slave. It has a select line that picks when the slave is active, and then it has a clock line. It comes out of the master, and that clock synchronizes the master and slave and determines when the bits are sampled in the slave and when the slave sends the bits back up to the master. So the clock pin on the actual Atmel chip exists, but the people who built the Arduino board didn't bother to build a trace from that to any external connector. So you have 4 USARTs that could run as an SPI link, but the clocks aren't connected to any pin that you can hook onto on the Arduino board. Now, fortunately, the Atmel processor, the package type that it has the leads around the outside. They're all visible and accessible on the board. So looking at the board, I could see that USART 2, the one I chose to use, has its clock coming out on pin 14. Pin 14 has no trace connecting it to anything else, but it is accessible. So what I decided to do was to pick some other connection that goes to one of the outside pins, the connectors on the Arduino board, and sacrifice it, disconnect it from its usual function, and instead come up with a wire jumper to connect that to the clock signal for the USART. I chose AREF, so there's a analog voltage reference pin that's used to do certain things with analog inputs that I don't need to use, and that's in a convenient location, so I could disconnect it and instead hook my wire up to it. So that AREF is pin 98 on the Atmel processor, so I'm going to simply lift that lead off of the PCB so it's no longer connected. Then I'm going to tack a wire onto pin 14, which is the USART clock for the SPI channel 2, and then run that wire around and hook it up to the connector that formerly was connected to the AREF signal. So I can now hook up an SPI link and communicate with my FPGA over that channel while the SD card is communicating over the normal SPI channel that's built into the Arduino board.